So in this short video, we're going to go over how you solve for the firm's cost function using the calculus-based methods. And I really want to emphasize that what we're doing here is we're taking an economic problem and then we're packaging it in such a way that we can use the optimization methods that we went over in the math bootcamp to solve the problem. So if you sort of get very used to using those three math methods, either taking the first order condition if you have a single variable function, if you're trying to maximize over two variables, then you take the partial derivative with respect to each variable and set it equal to 0. And if you're maximizing or minimizing some function subject to a constraint, then you can use one of the tools we went over there, including the Lagrange multiplier method. Right, so for all of these problems, I just want you to think which of those optimization tools is appropriate for helping solve this problem. Well, for the firm's problem of finding the cost function, what we're trying to do is we're trying to minimize the cost of producing subject to the constraint that at least some quantity Q is produced. Right? So that's what the problem is we're trying to figure out how to reduce or minimize the cost of producing a given quantity Q. Okay, so the constraint in this problem is just going to be rearranging the production function. We're going to have the quantity minus the amount that says that is produced according to the production function is going to be equal to 0. So basically, whatever this Q is, we're going to want to make sure that the firm produces that much, and we're going to try and minimize the cost of doing so. Okay, so perhaps the easiest way to sort of look at this problem or to frame this problem is to look at how you would solve it using the Lagrange multiplier method. That will clarify some of this. So I'm going to use a different symbol to represent the Lagrangian. Okay, the Lagrangian is equal to the thing that you're trying to maximize or minimize. Okay, so don't focus on what the functional form looks like. Think, what are you trying to maximize or minimize? Well, in this case, the firm is trying to minimize the cost of producing some amount. Okay, so the thing they're trying to maximize or minimize is this cost function, which is the wage times the amount of labor used plus the price of capital times the amount of capital used. And what the constraint is that we're multiplying lambda by is from the production function, that they're going to produce at least some quantity Q. So it's Q minus the quantity that would be produced according to the production function, which is this f of k and l. Okay, so that's what it is. Then you would just take your three partial derivatives, take the partial derivative with respect to L and set that equal to 0. Take the partial derivative with respect to K and set that equal to 0, and take the partial derivative of this Lagrangian with respect to the Lagrange multiplier lambda and set that equal to 0. Okay, and then you just have to solve the three equations for the three unknowns, L, K, and lambda, and the solution is going to be it's going to eventually yield L of Q, so some function that tells you how much labor you'd want to use as a function of the final output. You get the same thing for K, and then you plug that back into the cost function to get a cost function not in terms of the amount of labor and capital that you're using, but instead in terms of the final output, assuming that that output is produced at lowest feasible cost. Okay, now let's try going through this with a particular example. So let's assume that the wage rate is equal to 4, that the price of capital R is equal to 5, and the production function f of k and L is equal to k raised to the power of 0.5, L raised to the power of 0.4. Okay? So let's plug that into the Lagrangian. So we have the Lagrangian is equal to 4L plus 5K plus lambda times Q minus K to the 0.5 L to the 0.4. And then we're going to take our three partial derivatives. So the first one is the partial derivative of the Lagrangian with respect to L, and that just gives us 4 minus lambda k to the 0.5 times L to the minus 0.6 times 0.4, okay, and that's equal to 0. And in equation 2, we're going to take the partial derivative of this Lagrangian with respect to k, and that's going to give us 5 minus lambda k to the minus 0.5 L to the 0.4 times 0.5 is equal to 0. Okay. And then the third partial derivative, take the partial derivative of the Lagrangian with respect to lambda, just returns our constraint. So it's q minus k to the 0.5 L to the 0.4 is equal to 0. So we can look at various ways to solve it. I'm going to rearrange equations 1 and 2. So let me write 1 prime. I'm just going to add this second part here to both sides. So we're going to get 4 is equal to lambda k to the 0.5 L to the minus 0.6 times 0.4. And for 2 prime, we're going to do the same thing. I'm going to add this latter component to both sides, which gives us 5 is equal to lambda k to the minus 0.5 L to the 0.4 times 0.5. And now I'm going to use one of the solution tricks that we can use. We can say that 1 prime divided by 2 prime should hold. So that we take the left-hand side of 1 and divide it by the left-hand side of 2. That should be equal to the right-hand side of 1 divided by the right-hand side of 2. Okay, so that's going to give us 4/5 is equal to, let's see, lambdas cancel. K to the 0.5 divided by k to the minus 0.5 is simply k. L to the minus 0.6 divided by L to the 0.4 is 1 over L. And then 0.4 divided by 0.5 is equal to 4 over 5. Just multiply both the denominator and the numerator by 10. Okay, and you can see where this is going. We get that k is equal to L. So in this problem, when the firm is maximizing its output subject to some cost, or said the way we usually look at the mirror image, minimizing the cost of producing some quantity, they're going to choose equal amounts of capital of labor. Okay, we haven't finished solving the problem. We can now plug this into equation 3. I'm going to erase some of what I have here on the left-hand side to make some room here. Okay, so we're going to plug in k is equal to L in equation 3 to get rid of one of those variables, to get rid of k or L. And then we'll go through it. So let's plug in for k. So in the third equation, we have q minus k to the 0.5. Well, if we plug in for L, it just becomes L to the 0.5 times L to the 0.4. Right? So this part right here is what I plugged in. I plugged in L for k. Okay. And we know that's equal to 0. Okay, so if I just rearrange this a little bit, we get that L to the 0.9 is equal to Q, or L is equal to Q raised to the power of 1 divided by 0.9. And we know that L is equal to K, so this is also equal to K. Okay, so now we know how much labor and how much capital we'd want to use to produce a given final amount of output, Q. Okay, we just take whatever amount we want to produce, we raise it to the power of 1 over 0.9, and that tells us how much we want to use of each type of input. Okay, so the last thing we want to do is actually want to solve for the cost function. Okay, so remember the cost in terms of K and L was 4 times L, where 4 is the wage, plus the price of capital 5 times K. Okay. And so all we do is we plug in L is equal to Q raised to the power of 1 over 0.9, and K is also equal to that. So that gives us 4 times Q raised to the power of 1 divided by 0.9 plus 5 times Q raised to the power 1 over 0.9. And you could simplify this equation a little bit more. It's just 9 times Q raised to the power of 1 over 0.9. And that's a cost function. That's what we're looking for. Right? That's what we're trying to solve for so we can solve more complex problems later and actually try and maximize a firm's profits. Without having the cost function, we cannot do that. We cannot figure out what quantity of output is optimal. So I went through and I solved this problem where we're trying to minimize the firm's cost subject to the constraint of producing some arbitrary amount Q. I solved it using the Lagrange multiplier method. Really, you could use a variety of different methods to actually solve this problem. You could use the substitution method that we used in some of the other examples. You could use some of the intuition that are gained from the graphical analysis, mainly that the ratio of marginal products, that is the marginal product of labor divided by the marginal product of capital, is equal to the ratio of the prices of those two inputs. And then incorporate information from the production function to sort of impose the constraint. So there's a variety of different methods that you could use. What I really want to emphasize is that when you're trying to solve these problems, you have some economic problem that you're trying to solve, but you should be thinking which of the math tools that I learned in the math bootcamp lecture can I apply to this problem? And that will make it much easier to solve a lot more complex problems. So I'll end there for now. This is the last lecture in this series. In the next set of lectures, we'll look at types of costs and understanding how sort of the features of the cost function can be important in both regulatory and firm decisions.